We are live.
Okay, I think we're live now. Good morning, good afternoon, good evening, everyone. Thank you for tuning in. I am James from the DoraHacks team, and this is the workshop for the PancakeSwap and Brevis V4 Hookathon, which is live now. And you can get involved by heading over to DoraHacks.io. The link will be in the comments section, so check that out. Really exciting hackathon/hookathon that we've got going on at the moment. There are 20 days left for submission and a prize pool of $40,000. So a nice big prize pool. Just a bit of background on DoraHacks. We are the leading multi-chain developer community and hackathon organizer platform. And we're delighted to be the chosen platform for this hackathon with PancakeSwap and Brevis. You'll be building hooks on PancakeSwap, but I'll leave instructions on how to do that and what that involves to the Pancake and Brevis teams. So really happy to be hosting this. Guys, if you want to go ahead with the workshop, I'll hand over first to Chef Momo from PancakeSwap. Floor's yours.
Hey, thanks, James. Hello, everyone, and thank you all for being here today. I am excited to kick off this hackathon, and I've Chef Momo, product manager at PancakeSwap. Joining me today are Chef Miss, the smart contract lead at PancakeSwap, and Michael, who is the co-founder of Brevis. Our agenda for the day is as follows. So I'll start with a brief overview of PancakeSwap V4, followed by Chef Miss leading a hands-on session on developing a hook on V4, and after that, Michael will dive into Brevis's ZK coprocessor and demonstrate how to integrate hooks with ZK coprocessor. So post that, we'll wrap up with the Q&A session to address any questions you may have. Yeah, so I'll just quickly share my screen. Yeah, okay. So yeah, let's begin. Um, I'll quickly revisit PancakeSwap journey, and then we'll talk about V4. So we launched version 1 in 2020, end of the year. Uh, and we were the first X1 BNB chain where we deployed B2 style liquidity pools. Shortly after, in 2021, we launched the version 2 where we supported stable swaps and also implemented cake buyback and burn. Between both the versions, we achieved quite a few milestones where we were the first $1 billion TVL protocol on BNB chain, and then we reached a peak TVL of $8 billion and also held over for 50% market share of trading volume across all the dexes. Um, Last year, we launched version 3, which supported the CLMM style AMM pools and expanded to 9 plus chains. And Cake turned deflationary as well, where we introduced weak cake gauge system for cake incentivization. The overall stats, in terms of overall stats, we've serviced over 42 million users till date, and have processed around $850 billion of trading volume across 1.5 billion trades till date. So yeah, and this year we announced PancakeSwap V4, and let's look at why we need it. So, as you might be aware, previous version, which is the version 3, was limited in kind of having custom features or new MM designs, and it was pretty rigid in terms of what's supposed to do. Uh, and also, it had like huge gas costs, so it was challenging for developers and DeFi protocols to build upon us. So, what do we want to achieve with V4? We want to become the core liquidity infrastructure for DeFi, where we let the developers and the protocols uh, add any custom features to the pools through hooks. And we have also added a lot of gas optimization techniques for scalability and cost effectiveness for the user base. And how do we do it? We do it through the three-layered modular architecture, where we have an accounting layer which takes care of the settlement with the users, the AMM layer which support different pool types. So at launch, we'll be supporting the concentrated liquidity AMM, the liquidity book AMM, and we can add any kind of pricing curve going forward without re-implementing the core protocol. And the custom layer, which is the hooks. So through hooks, you can basically add any feature to a liquidity pool and launch it. So it doesn't need any kind of re-implementation of the protocol, and there could be a variety of features you could implement through hooks. Um, And all of this is done with a lot of gas optimizations, and techniques like singleton flash accounting will definitely have benefits for the users, uh, and also the integrators. Now, in a nutshell, on if I have to, what are the key features for the developers and protocols? So like we discussed, the hooks and the new MA models, which the developers could kind of play around with, and then they get to benefit from PancakeSwap user base and deep liquidity, and they can also create a revenue stream, the hook fee. For traders and LPs, it's streamline operations, gas savings, range of features introduced through hooks, and a variety of designs like we discussed with unlimited fee tiers. So yeah, and before I hand it over to Chef Mist, this is Hookathon is a part of PancakeSwap $500,000 developer program, which is specifically for V4. And there are like quite a few initiatives we have been kind of working on, as well as will announce in the future. So it's just not just hackathon. Once you kind of participate in this, get familiar with the V4 code base, there's a lot to come. So yeah, stay tuned, and yeah, this is going to be a great journey with all of you guys. So I'll hand it over to Chef Mess now to have a walkthrough for how to create a hook on PancakeSwap V4.
Hey, thanks, Momo. So, let me just share my screen. All right, for the next 15-20 minutes, welcome to the workshop on developing a hook in PancakeSwap V4. So I'm Chef Miss, smart contract lead with the team. So Momo has already shared the high-level architectures. So just to save time, I will skip these particular slides. I just want to highlight in V4, there are two pool types that Momo has mentioned, the concentrated liquidity type as well as the bean type. So let's talk about the difference between these two types. For concentrated liquidity, if you're familiar with PancakeSwap V3, it is similar. Basically, the LP and liquidity at a specific price range, and the liquidity is concentrated in a price range. It provides more capital efficiency to the LPs and better price execution to the traders as compared to V2, where liquidity was spread across the entire price range from 0 to infinity. On the right is the bean type, which follow X plus Y equal to K logic within a bean. When you add liquidity to the bean type, liquidity is added into separate beans in a stack manner. So for example, if this is ETH USDC pool, let's assume liquidity for ETH 2900 is this, 2950 here, 3000 here, 3050 is here. When Bob is adding liquidity from 2900 to 3050, he's adding liquidity to actually 4 different beans. So assume ETH is at 3000 right now. When a user is trying to buy ETH, they'll swap their USDC for ETH in this particular bin. And if there's sufficient liquidity to execute the entire order within this bin, the swap will have a single price of execution with 0 trading slippage. So that's the one benefit of bin type liquidity pool. However, if there are not enough liquidity in this bin, the swap will cross over to the next bin over here. That's where the price impact will happen as the ETH price jump from 3000 to 3050. So in our developer docs, you are able to find more details on these two pool types and the scenario on which one may be a better fit for traders and liquidity providers. So next, what are hooks? Think of hooks as executing callbacks during transactions. There are 10 possible callbacks before and after 5 key actions, which happens in an NAM. The key actions you can see over here includes related callbacks like initializing the pool, swaps, liquidity related, as well as donates. And the thing about all this definition is that they are immutable. So for example, if you define a pool with just before swap callbacks only, you can't add after swap callbacks down the road. So you will have to recreate a new pool with both before and after swap permissions. So just think very clearly about the kind of hooks that you want. When it goes live, you can't change the permission anymore. So what can you do in callbacks? There are some ideas here, Swapfee discount limit orders that you may have guessed. And in this hackathon, definitely looking forward to what kind of Brevis powered hook that you can create. So next, this is a very simple sequence diagram of how a user is performing a swap and how the hook is being called. On the left here, you can see it's a user trying to interact with the universal router to perform a swap. So first, I call universal router.execute, and then before doing anything in default, they need to obtain a log from the vault. So we call vault.log, and the vault will then return a log acquired. So after which the routers can then call pool managers to perform a swap. So this is where the magics happen. Basically, pool managers will check for this particular pool, is there a hook? And if there's a hook, did the hook register before swap permission? And if it does, then it will call hook.before swap, passing in all these related parameters over. The hook can do whatever it wants, after which it returns. The pool managers will then use its internal library to actually calculate, given this amount in, how much amount out to be given. And then it will check again, right, for this pool, is there a hook with after swap permission? If yes, call hook.afterswaps. And then after all this, you will then update the delta, which is the amount in, amount out for this swap to the vault, as well as the routers. And then finally, the routers will then take token from the users, transfers to the vault, and take token from the vault, transfers to the users. That concludes the swap here. So hopefully this gives a bit of illustrations about where hooks are being caught in a swap example. So with that being said, in this workshop, we do a very simple hook on CL pool types. So in PancakeSwap ecosystem, there's a token called vCake. This token serves a crucial role in the governance. Users can use vCake to vote, and they get vCake by voting login cake. So in our example hook, if the users hold this vCake, we want to provide them 50% swap fee discounts. So in the next few slides, let's look at some concepts on how to even do this kind of hooks here. So the first we need to do is to store the default swap fee of the hook. And in order to initialize a new pool in default, users actually call this method pool managers.initialize, passing in the pool key, the starting price, and then this is what we can pass to the hook, which is the byte32 hook data. So we'll use this to call to initialize a new pool by saying this particular pool default swap fee is 3,000, which is 0.3%. And then this data will flow to hook in the after initialize callbacks. And then this is where the hook can actually decode the value and store to know that for this pool, the default swap fee is 3,000. All right, that's the first part, which is using after initialize to store the default swap fee. Next, now that we have stored the default swap fee, how can we give it 50% discount whenever users do a swap? We can use the before swap callbacks. So in the before swap callbacks, you will pass in a few parameters, but what you need to return are 3 different return values. First, the byte 4 selectors to let pool managers know, hey, this execution is fine. Next, before swap deltas. This is for use cases where the hook want to take a fee or give extra token, but that's not in our use case, so we just return 0 for this. And the last parameter, the LP fee override, this is where we can actually specify for this particular swap, we want to use a different swap fee. So we can potentially take the default swap fee divided by 2 to give 50% swap fee discount. So that's the rough idea to implement this particular hook. So next is to get started, you can just simply follow these instructions. Go to this hook template repositories and then click use this template, forge install, forge test. If you see the test passing means your setup is completed. So let me just start the little workshop to actually do this particular hook here. So this is the hooks template repositories. So if you come to here, you can see there's this button, use this template. Click on it, it will fork this repositories to your own GitHub here. So if you have set up everything properly, if you run forge tests, you should see all these tests passing. Okay, let's quickly run through what's in the hooks template before we start developing our hooks. So if you look at the hooks template folders, you will see that source and test. Within there are 2 folders, the pool bean and the pool CLs. So depending on what hooks you are creating for, for the bean type, you'll focus on pool bean folders. If you are developing a hook for the CL types, you'll focus on the pool CL folders. So let's, since this workshop is about consensual liquidity hooks, let's look at these folders instead. Within the pool CL folders, there's the base hooks. So think of this as the hooks that you abstract contract that you inherit for all your hooks. It's just contains all the helper methods that your hook needs and what you can override. For example, all these different callbacks that you can potentially override. And then here, CL counter hooks. This is an example hooks that we put in the hooks template for you to reference. So you can see it's just a very simple hook that counts the number of time it's being caught. And you can see it uses the base hooks. And over here, what we want to do is to count how many times before after liquidity is caught, before after swap is caught. So here we have a mapping. And then next is this method, hook registration bit map. So this is a very important method that all hooks need to implement. It basically defines your hook, what are the callbacks that you need. So in this case, because we record 4 different kind of counts, we actually say true to before liquidity, after liquidity, and before and after swaps. So the rest we leave it as false. And for each callback that you need to implement the methods. Yeah. So you can see 1, 2, 3, and 4. And then the implementation is pretty straightforward in there. We just simply go to the mapping plus plus. So that's all this counter hook does. And then if you look at the test, within there we have test utils. So this has a lot of helper methods for you. Basically, yes, one method called deploy contracts with tokens. It basically just deploy all the contracts that will help you in your testings, like the vault, the pool managers, the position manager, and the routers, so on and so forth. And of course, it has other helper methods like adding liquidity. I'm not sure if it's too small. Let me just expand it. Adding liquidity, decrease liquidity, swaps related, all these helper methods. So let's look at a test, how to write a test for hook. If you're familiar with Foundry, over here, what we do in the setup, we actually deploying all the contracts to the tokens. We create a hook, and this is how in PancakeSwap v4, how a pool definition looks like. It basically has the token 0, token 1, the hook address. If there's no hook, then it's address 0. The pool managers, the fee over here. So if you specify a number over here, this will be a fixed fee pool. So in this case, it's a 0.3% fixed fee pool. And then over here, the parameters is where you define what are the hooks permission required by doing this, hook get hook registration bit map, and as well as setting a tick spacing for this particular pool. And then this is what we do to initialize the pool. We assume it's a stablecoin pair. So that's why it's 1-to-1 ratio. And to write the test, we just simply check the liquidity and the swap, whether it's caught. So within the liquidity, we check before and after liquidity count is 0. And then we use the helper method to add liquidity. This is the helper method from CL test utils. We verify the count is 1. So that means the hook is being caught successfully and the counter is updated. Likewise for swap, we add some liquidity to the pool. We verify before its count is 0. We do a simple swap. We verify the count is 1. So yeah, this is a very simple example of how to write counter hooks. So let's proceed and write the swap fee discount hooks. Just to do a quick 1-minute recap, we need 2 permissions. One is in the after initialize to store the default swap fee for the pool, and one is before swap, where we actually give 50% swap fee discount. Okay, let me get started. So what I'll do is I'll just copy and paste this, and then I'll just name it PE kick swap fee discount hook, and then update this theme. And I have some comments that I created, so I'll just overwrite this comment. Okay, so basically, this is a description of what we're gonna build. Let's make it bigger. I'll delete all the mappings that we don't need. And because we only need after initialize and before swaps, so let me just set false for all those that is not relevant. So after initialize is true, before swap is true, the rest we leave it as false. And then of course we can just delete all the methods that we don't need. We just need before swap and after initialize. So let me just copy over the after initialize. Okay, and then I need to return this dot after initialize dot selectors. So if you recall over here, this is where we store the default swap fee that's passed in the hook data. So let's write in the default swap fee. Yep, ADI decode hook data. And then we need to store this in a mapping. So pool ID to LP fee. Okay, so for each pool, we store the default swap fee after initialize. Now, when a user is doing a swap, we want to give 50% swap fee discount. So first, what we can do is retrieve the LP fee for the default swap fee for this pool, and then we check if the VCake, the balance of the guy who actually initiated these transactions, have more than 1 Ether. Then we can say the LP fee equal to LP fee divided by 2, 50% off basically. And then to return it is the last parameter over here. So instead of 0, we return the LP fee override. But in order to override the LP fees, we also need to set a flag. LP fee library override fee flag. And then I think over here I use VCake. So in my constructors, I'll need to actually store what is the VCake address. So I'll just pass in a VCake. And then let me just copy and paste some parameters that I need. The mapping, the pool ID. And then let me just put the VCake as well as because I'm using IVCake, so there's an interface that is required over here. Yep, so this roughly looks like the hook that we want. When our users come in to swap, we will check if they are VCake holders. If they are, we'll give them 50% swap discounts. Okay, looks good, I guess. Okay, so now we have written the hook. Let's quickly run through how to write the test. So likewise, I'll copy this file, rename it as swap fee discount hook test. And then I'll update the import to import the VCake swap fee discount. And over here it should be the swap fee discount hook. And then because we need a VCake as well, so I will just simply use ERC20 to block the VCake, and then I'll have at least to act as a VCake holders. And over here, we just update the constructors to VCake discount hook, and then passing in the address VCake. Next, for this particular pool, because it's no longer a fixed fee pool, so for the fee, we cannot put a number anymore. So this is where we actually indicate this is a dynamic fee by using LP fee library.dynamic fee flag. So this will let pool managers know that for this particular pool, the fee is dynamic there. And then the rest, we can leave it the same. The next part is the initialize. If you recall, we need to pass in the default swap fee in the hook data. So this is how it should look like. Basically, the difference is that we initialize the pool at 1-to-1 as well. It's just that in the hook data, I'll put a default swap fee. Okay, and then let me delete the existing test. So for test, in this case, we need to test as a VCake holders as well as a non-VCake holders. So let's do a test that is testing as a non-VCake holders, and then we test as a VCake holders. And then for both the tests, what they need to do is to do a swap. So I'll first just simply, to save time, copy a helper method that does a swap. So over here, this particular swap method just check the balance token 1 of Alice before the swap, and then Alice will perform a swap of token 0 to token 1, passing in 1 ethers, and then we check how much token 1 Alice has after the swap, and that is actually the amount out that Alice has gotten. Okay, so for both of them, they need to do a swap. So let's perform a swap in here. But for Alice, for the VCake holders, we actually need to mint Alice on VCake, so she can get swap fee discounts. And let's do some simple assertions. So if you're non-VCake holders, your amount out should be less than 0.997 because of the 0.3% swap fee, as well as potentially some trading slippage. But if you are VCake holders, you can actually verify something like this. Your amount out should be greater than this time round, 997, because your swap fee is only 0.15%, but it should be less than 9985 if there's a 0.15% swap fee. So of course, in the real world, when you write tests, you should verify the exact numbers, yeah. So yeah, and then lastly, let me just add in some helper over here. This is around before every test, we add liquidity to the pool, and then we do some approval of at least to the routers, and then we give at least some tokens to do a trade. So if everything is working fine, if you run forge test, there is declaration error copy. All right, my naming pancakes. And then the import. All right, I didn't import the LPC libraries. So let me just import the LPC libraries over here as well. Yep, it takes some time to compile, but once the compilation finished, and if you see a test case passing, that means the hook is created, yep, successfully. Yep, if everything works, you should see something like this with the test passing. So yep, that's roughly from us, from PancakeSwap. Let me just share a bit more. These are the links that we use in the demo. So what I would recommend is to actually look heavily at our developer docs. What I have introduced is a very simple hooks. But if you spend more time to look at a different guide that we have, there's actually a lot more use cases that hooks that you can look at over here. Yep. Thank you very much. I'll pass it over to Michael.
Awesome. Thank you, Mr. for the great introduction. Let me try to see if I can bring this to the stage first. So can I bring the other slides to the stage first? Is there a way to do this? All right. Awesome. Cool. Well, thank you for that great, introduction and also very detailed tutorial about how to build a Pancake V4 hook. And here I will basically kind of discuss from both high level and also from kind of very hands-on perspective on how to build PancakeSwap hooks powered by Brevis. Well, the first question we need to answer is why, right? So why do we need to actually to build PancakeSwap hooks powered by Brevis ZK coprocessor? Well, let's take a very, very simple example here. So we also like the power of dynamic fee hooks, like before swap hooks, implemented as before swap hooks. But let's say we want to build something very simple here. We want to build a trader loyalty program which exists in every centralized exchanges, where you want to reward a trader by lowering the trader fee or trading fee in the next 30 days if the trader has traded like a certain amount of volume and reaching a certain VIP tier in the previous 30 days, right? So it's a very, very simple example. But you would imagine that this can be built with a hook-based architecture because after all, we have the capability to do dynamic fee. But unfortunately, no, because if you want to actually implement this, you need to let the blockchain smart contract itself access the historical trading events of the users. Now, accessing that directly in smart contract involves essentially verifying a very large amount of Merkle proofs. Basically, you have the block header now, but you want to verify if a certain transaction or if a certain event actually happened in the past, then you need to essentially kind of rebuild the entire block header construction process to the current date to say, okay, there is a transaction in the past like 10 blocks, and then the Merkle inclusion proof can prove that it was included in a certain block. And then finally, that particular block is actually part of the entire blockchain history based on the current block hash, right? Because after all, the block hash is an encapsulation and is a compression of the entire blockchain state. But doing that in smart contract is just not feasible. So what we have now is that we have smart contract. We have a modular, DeFi architecture that is enabled by PancakeSwap. But we need a powerful tool to actually leverage that type of architecture by allowing smart contract developers, and users to actually access these historical data and do meaningful and complex computation on top of them and feed that data back to the blockchain and back to the smart contract to enable features like dynamic fee. right? So this is like why this is a challenge right now. Without Brevis, because as a smart contract, there's no way for you to have trust-free access, and computation on historical on-chain data such as events, transactions, and storage states. So, Brevis here is to solve that. Brevis is a ZK coprocessor that is capable of generating ZK proof of arbitrary computation on any type of historical on-chain data, including events, transactions, trades, and even block data like account, nonce and everything. So the important thing here is that, because there's a ZK proof generated, you can actually utilize the result of the computation in a trust-free way, because the entire computation process is encapsulated in ZK end-to-end. So using Brevis is very simple. From a high level, you specify what type of data you want to read and what kind of computation you want to run on top of these data. And what Brevis will do is that Brevis will do two things. One is it will generate a attestation or of a validity proof that these data you want to access actually exist in the history of blockchain, right? So for example, this user actually swapped this amount of USDT to USDC. And it will also generate a validity proof using ZK of the computation process itself, right? So if you want to basically say add up all the trade amount of a user's previous trade on PancakeSwap v4, you can do that, and Brevis will actually generate a zero proof showing that, hey, look, this is the amount of this is the actual trading volume of this particular user, and there's no way that this number can be wrong. Now, finally, with the proof and also the final output of the computation result, you can submit all of that as a package to the blockchain smart contract. In this case, a PancakeSwap v4 hook contract, and the hook contract will be able to verify that proof very cheaply, because verifying a proof of arbitrary kind of a computation, even though the computation can be super complex, is constant cost, right? So this is where the cost reduction comes from. And once that proof is verified, you can store the value, for example, of a user trading volume in the hook contract, and the hook contract will be able to record that and trigger a user's corresponding VIP tier when the next swap comes, right? So if a user make a new swap, the swap can trigger a before swap hook and look into the swap, look into the hook which records the user's actual trading volume and determine, okay, this user is actually a VIP and therefore should be given like a trader discount, a trading fee discount. So like this is basically how the entire process works from a high level. As I mentioned, you can access any type of blockchain data, and it's very easy to do that, and also do arbitrary type of computation using a very, very simple to use API. You don't need to know anything about ZK circuit writing, because we essentially we abstracted away all the details of the low level circuit, and they presented the developer with a very, very easy to use high level SDK with like data stream abstraction. And then finally, you write the smart contract to actually handle the use case and logic in the smart contract land via callbacks. So if you use the same thing to build the same kind of a trading volume discount, trading volume based discount feature with Brevis, the process is very simple, right? So like instead of doing everything in the smart contract, the smart contract can call a get trading volume function, and this function will be monitored by an off-chain component that is written using Brevis. And once that event is triggered, and the entire off-chain component will be put into work, and the entire off-chain computation process will be done, and the ZK proof will be generated, and callback will be issued back to the whole contract to say, okay, now I have the trading volume, and also the proof process reach the trading volume. Once that is recorded, the user will be able to continue to swap with a discounted fee. So that's a very, very simple process to do that. And with this architecture, the cost is reduced in a drastic way. The cost of computing, let's say 1,000, a user with 1,000 trade is only $1.4, and the latency is like 100 seconds. So there are some hook ideas other than the trading volume based fee discount. So for example, you can actually build things LVR, compensation based on market volatility, which is essentially also a dynamic fee based hook, but the business logic is not dependent on trading volume, but instead based on the entire market's volatility. But you can actually add, compose both of these together as a single hook, and achieve both LVR protection and also high user retention, and also kind of a high market efficiency, right? So you can also do retrospective mining reward based on the fee generated in each of the LP position, because now instead of only be able to reward LP based on the time length of their liquidity deposit, you can retrospectively examine each LP's fee contribution to the pool, and then precisely target those LPs who actually contributed a lot of fees, to the protocol. This is really beneficial for the entire pool, because you're directly rewarding the LP who hold the ground when the market is actually volatile, because there are actually a lot of LPs who will withdraw their liquidity when the market is becoming volatile, but will actually put the liquidity back when the market is stable, right? So you can also do token holding based fee discount. Let's say if you are a protocol with a governance token, and if there are a lot of users already holding your governance token, if they want to buy the governance token directly from the DEXs, you would imagine they should be getting a priority and a fee discount because they are already a holder and active participants in the governance process and in the protocol security, for example, right? So, and there are things like token gating based pools, based on certain historical activities. Let's say this user is a very, very big trader of certain type of token, or this user is a proven kind of a whale or proven OG trader for certain type of applications. Then you can essentially kind of gate your pool by allowing these OG status users to become a liquidity provider and become the trader for the pool earlier than the general public, right? So what you can also do is that you can do user acquisition through on-chain user profiling to essentially say, okay, instead of just doing dynamic fee based on the current pool's user behavior, I want to actually attract other users from other different protocols to use my pool or my DEXs built on top of Pancake v4. Now, what you can do is you can allow users to generate ZK proof that he is a big trader or holder of tokens in some other similar protocols, and you essentially migrate their VIP status to PancakeSwap to allow them to get a fee discount, and then immediately bootstrap a very, very efficient market structure, because oftentimes these users are professional market makers. If you offer them lower fees, it is beneficial for the entire market, even for smaller traders to get higher, better pricing in PancakeSwap as well. So there are so many ideas once you can access the historical value of, or the historical user activities and the historical value of the pool protocol, of the pool and also the users. So this is just kind of a very high level introduction of how Brevis can be combined with Pancake. Now I'm going to switch gear and talk about how we can actually integrate this in a code level. James, can you help me? Yeah, that would be great. Thank you. So now let's get to how this actually works from kind of a implementation perspective, right? So as I mentioned, in Brevis there are actually two parts to the entire business logic. The first is how you want to do the computation, like what if you have all these data, what type of computation you want to run on top of that. The second part is that whether the input of the computation is actually correct and accurate, right? So now how to build with Brevis also is split in this two part. If you follow the if you follow kind of the flow here, let's start from the off-chain component here, where you have the application services. The application service, you already have two parts. One is the data access part, where the data access component is still getting all the necessary blockchain data from a third-party indexer. Let's say you're using Alchemy, you're using Dune Analytics, you can keep using that to say, okay, I want to compute the user trading volume, but of course I need to know all the user trading events, right? So I need to get that from somewhere. you can still get that from any kind of indexing solution you have. And then assuming all the data is actually correct and complete, then what you can do is that you can essentially say, okay, now I'm going to do the computation to generate an application ZK proof that contains the business logic to calculate what is the trading volume for this user based on the event that I got. Right. So, and then what happens is that after that, you get once what we call subproof. This proof is basically just describing this user has if all these data is actually correct, then the trading volume of this user is like that, let's say $3 million. But the next step here is to actually send all the proposed data and the application subproof to a Brevis backend. In the future, this will be a Brevis prover network, but right now it's kind of through a Brevis gateway that you can send it to a gateway that is containing our SDK doc. And after that, you're done. Like, you don't need to actually worry about the subsequent proving process. What happens underlying is that Brevis service will prove both the application logic and also the data input are actually accurate. So what this means is that this guy actually Brevis will actually be able to prove that all these trade events happened in the past, and also the sum of the trade event amount is actually this particular volume. And what happens after is that once a ZK proof is generated, so it will be posted to a Brevis verifier contract. So the Brevis verifier contract is a universal verifier contract, can verify any proof generated by Brevis. And it will be binded when you're doing the development, when you deploy a application contract to bind the particular application logic with the corresponding Brevis contract via something called a verification key. And once a Brevis contract verifies a certain proof is corresponding to a particular verification key, it knows where to send the callback to. So it will send the callback containing the trading volume data, for example, to your application contract. And in this particular case, the application contract can be a hook contract. Then the hook contract can essentially record what is a trading volume of this particular user and record that with a corresponding fee discount number. And the next time the user comes to the pool and make a swap, the before swap hook will be looked up, and then a dynamic fee will be written into the entire swapping flow. So this is like kind of from an end-to-end overview how a hook can be built with Brevis, using PancakeV4 architecture. The thing I want to highlight here is that these blue boxes, the application contract to handle the callback, and the application service where you write how you want to compute on these data, are the parts that you need to write as a developer. All the gray part you don't need to worry about. That's kind of handled transparently by Brevis. So, for the data access part, we have a Go-based SDK, but we also understand a lot of the developers comes from a JavaScript TypeScript background. So what we also provide, as you will see in the documentation, is a TypeScript SDK, where you can use the TypeScript API to invoke the prover service, where you can just simply write a very, very simple Go function, and then there is a very standard way to spin up the prover service, so you don't need to actually worry about spinning up any type of Go infrastructure on your own. And this is also kind of hopefully make this entire process easier for JavaScript and TypeScript developers. So now let's talk about how this actually is implemented, right? So as I mentioned, there are two steps. Let's talk about how to add the source data first. So this is very simple. It's basically just an instantiate a prover service, and the proof request object and class is where a lot of these kind of business logic is going to happen. So for example, if we're looking at this PancakeSwap B4 event, which is like a swap event, and if we want to add these type of event into the data, for computation proof generation, how this works is that we will do SDK log field data to generate like what is kind of the log field, and what is the log index, which is like the number of events this particular event is in this transaction, and the event ID, which identifies what is this event. In this particular case, this is a swap event. And the important thing here is to understand the field index, right? So if it is an index, if it is like one of the topics, then the field index will be 1, because the field index is 0 here is a topic itself. And what is the value of this particular value is the swapper or the sender of the transaction, right? For example, this is like the field that you care about. You specify what type of field you care about. And the second field you care about is actually the log field data of the swap amount, right? So like similarly, in this particular case, the log index is still 1, because this entire event is the first event in the transaction, and the event ID is also the same. But because this particular data contained here is not part of the topic event or index event, so you have each topic false, and the field index is just like the LP encoding field index, the first field, and this part is to just specify this is the first 32 byte of data you care about, which is like the swap amount. So all these data, and all these kind of code base will be open source. It's supposed to be open source if you want to build a Brevis powered Uniswap PancakeSwap hook, so that you can understand, your users will be able to understand, okay, and the auditors will be able to verify that, okay, these data are actually what's included in the entire business logic calculation, and this is indeed matching the business logic of volume calculation. So this is a part of how you add the relevant field and relevant data into consideration. Now you add all this data already. This next step is to actually write the business logic to compute on top of these data, right? So the first step before the computation often is sanity checks, because what Brevis does is as you probably noticed that this kind of a data access and data data fulfillment process doesn't actually come with like filter or business logic to check whether the data is valid or not. You could actually, in this step, in theory, add some data that is just garbage, right? So if you want to add a data that exists but is not part of PancakeSwap's swap event, but from some other kind of a smart contract, you can add that. But this part of the sanity check is where you want to actually filter and check the data validity that is passed into the computation step. So for example, here you have a lot of like easy equal, to basically check whether the events are all belonging to the user you care about, whether this events are all coming from the pool you care about, and so on and so forth. So this sanity check part is very important, and we have the API to do that. Underlying this will be converted into ZK circuit. So this part is not just a simple kind of a sanity checks out of the ZK land. This is actually part of the ZK computing logic itself as well. Now, after the sanity check, the computation process itself is actually quite simple. So for example, here we provide a data stream based API where you can apply things map, reduce, filter, group by, sort, zip, this type of primitives with customized functions. For example, here you're applying a map function, which basically is a for loop. So there's no for loop. That's kind of the only inconvenient thing about this. If you want to use for loop, you just use map. And you say, okay, I want to essentially loop through all the receipt and extract what is the block number from all these receipts. So this is what this does, that it maps the received data to extract the receipt data's block number as a new array. And then this part is similar, where you basically say, okay, you get like each of the receipts the actual swap volume to say, you remember how we defined the field 0 for the receipt. This is kind of how we kind of defined the field 0 to say, okay, this is the field that I care about this particular event, and you want to kind of essentially decode. This is to tell the ZK circuit to actually decode that particular field and prove that decode is actually correct. And this is basically to get all the trade amount from all the receipt. And finally, you can just sum up all the volumes as a trading volume. So as you can see, the entire process to actually compute the user trading volume is that simple here. And now after the computation is done, you need to decide what type of data you want to output. And these output data are the data that will be posted back to the blockchain as callbacks. And this is what will be contained in them. So, for example, you can essentially output like byte 32. You can output int with different kind of a width, and also output typed variables like address format. And all of these output will be decoded when it reaches the blockchain smart contract. And so this is the part that you actually implement the callback handler function in your smart contract to essentially say, okay, once the proof is generated, the proof result will be posted back and called the handle proof result. When this particular function is called, the proof is already verified. So you don't need to actually write any verification logic in your smart contract. That is also handled by the entire Brevis SDK. All you need to do is to actually decode this particular output. For example, this is like the encoding process of the output when you write the circuit. So you basically reverse the entire process by peeling out all these kind of a different data parts from the encoded like call data. And then you can essentially kind of use that in your smart contract to essentially say, okay, now I know what is the trading fee, what is this particular user. I know this is like between what start block and end block. Now I know what is like the qualified trading volume discount for this user and for how long, right? So you can record all of that in your hook contract and and make that functional. So just to highlight a few things to note, when integrating with PancakeSwap v4's hook, especially if you want to build something related to dynamic fee. I think Chef Mist also briefly mentioned this, but to just highlight this, because this is probably one of the most popular type of hooks, the pool key.fee should be always fixed as this number for pools with dynamic fee. Otherwise, it won't actually work properly. And you want to actually save the actual base fee inside the hook contract itself. And the get hooks registration bitmap for the before swap value should return true for your hook. And in the before swap hook, the return value of the dynamic fee should be like in this format, right? So like this is just some of the highlights we want to highlight to the developers for you to understand and know that these are some of the potential caveats that might be easy to miss when you're combining Brevis with the PancakeSwap v4. And this is like what we have done when building and collaborating with PancakeSwap as well. So what we are ideally looking for in this hackathon is that you can build this point and click interface to easily deploy hooks based on the certain parameters that you want, right? For example, this is a very simple application user interface to deploy a trading volume-based fee discount hook to say what is like the token zero's name, what is like the token zero's address, token one name and token one address, what is like the deployed chain, what is like the pool-based fee, what are the VIP tiers and their corresponding trading volume and trading fee, what is the VIP tier activated duration, what is like the consideration for the time length of the VIP status, and so on and so forth. So like once you have this, the intention of this is that your hook contract and your hook implementation can be built and used by a lot of pool deployers who are interested in deploying their pools on PancakeSwap and enabled with like DoraHook, right? So this is for example, like we basically built this nice portal for pool deployers to monitor their hooks statistics and also understand what is the kind of usage scenario and configuration for each of their hooks. So try to build towards this, but of course for this hackathon we're looking for the core of the implementation. We're looking for the end-to-end working process to say, okay, a proof can be generated and can be written back to the hook contract, and certain function can be triggered during the before swap and post swap hook and things like this. So we're not exactly looking for a super full-fledged implementation with UI and everything, but as Chef Momo also mentioned, there is a very, very significant grant program from PancakeSwap V4, and we will also be matching with like our side of a grant as well after the hackathon. So we're outside of just like the 40K prizes, we're looking for amazing teams to actually become one of the first pioneers in the modular DeFi and DEX space to build with that together in long term. So all of these code bases that I shared with just now is accessible via our public SDK repo. In the SDK repo, there is a example folder that you can look into various different type of implementations and kind of solutions end to end, and also definitely access our public documentation hosted at docs.brevis.network. And we are very much available on our Telegram and also Discord. If you have any question, just ask there. Someone will definitely help. So with that, I conclude this quick tutorial.
Okay, thank you, Michael, and thanks Chef Mist and Chef Momo from PancakeSwap as well for that really in-depth workshop. I'm sure all the hackers now have got a great idea about how to build their hooks. And just a reminder from me then, from the DoraHacks end, this hackathon has got 20 days left. Submissions close on the 30th of September, but then there'll be the follow-up and the judging and the announcements after that. And the prizes look really sweet. There's a 40K prize pool, first prize being 12K, second being 10K, third 8K, and so on down to the fifth prize. So make sure you get involved. All the links are in the comments section. You can join in the Telegram or Discord. If you've got any questions, feel free to reach out to DoraHacks on DoraHacks official Telegram or the Discord as well if you've got any questions about submission. But guys, that was amazing. Anything you want to add from the Pancake side?
Yeah, on our side, as we have
Is the pool
sorry.
So I think we've just got some questions coming in from the community. So I'm not sure if he's been added to the call, but we've got, is the pool creation UI already developed with a hook, or was it just an example?
So yeah, that for that particular hook,
one
there's like a kind of a UI that is available, but that is just kind of for the trading volume based hook. And we're very much happy to, if you're interested in building something like this, we're very much happy to kind of work with you and build together with you to integrate you and also kind of maybe expand that UI to include the hook idea that you have, or like build a separate UI, but we just want to support you whatever we can.
Yeah, thanks, Michael. Any other questions for live listeners, just send them in the comments and we'll get them asked over to the teams now if you've got them. Otherwise, you can reach out afterwards, as I said, comment on this video or through the Telegram or Discord channels that we've got. Just give you a few seconds if there's any more questions coming through. In the meantime, yeah, sorry to interrupt you, Momo or Mist. Anything you want to add before we wrap this up?
Yeah, so we've mentioned all the relevant resources and links on the DoraHacks dashboard under the details section. So you'll be able to find all the stuff in there. And then please join the Discord server as well for any questions. We'll be happy to address those queries. Yeah, that's pretty much on our side.
Great. Okay. Thanks, guys. Michael, anything you want to add before we wrap this up?
Nothing else. We're just super excited and looking. We know there are already 3-4 teams that are interested and start to ask questions. And we're super excited to see what hackers come up with in this amazing hackathon.
Yeah, great. So hackers, go ahead and get registered. You can submit your buildle with your hook now if you want, and update it right until the deadline of submissions on the 30th of September. So if you want to upload it now, just with the bare bones there, and then update it as the hackathon progresses, that's also fine. Or you can get everything in place before submitting your project. Either way is fine. But I can't wait to see the hooks that everyone's building. So yeah, let's recap after the hackathon ends. Thanks, everyone.
Thank you, guys.
Thanks, everyone.